name is Elliot Borshow, and along with Amy Hayes and Paul Hooley, we will be presenting our project on solar impulse. Our aim is to present an interdisciplinary engineering project and its impact on our society. We will be focusing on the fields of mechanical, materials, and electrical engineering. Our presentation follows the journey of solar impulse on its actual journey around the globe, which began here in Abu Dhabi. Solar Impulse is a Swiss-based engineering project which has developed an experimental solar-powered plane. The plane itself is a single-seat monoplane, which is powered solely by photovoltaic cells. The project is led by Bertrand Piccard and André Borschberg, who were the main pilots of the aircraft during its 15-month-long journey. Although remaining in the northern hemisphere, Solar Impulse successfully circumnavigated the globe in 2015 and 2016. The goal of the project was to bring attention to clean technologies and show their capabilities.
When designing Solar Impulse, the main limitation was the amount of energy that could be provided by the solar-powered motors. The plane had to fly around the world on 4 17.4 horsepower motors. Despite the power limitations, Solar Impulse was able to achieve altitudes of 9,000 meters and speeds of 90 kilometers per hour. The plane also had the ability to coast at night at speeds of around 37 kilometers per hour. The main contribution of mechanical design was altering the weight and proportions of the plane. Engineers had to make the most of what energy was provided from the solar panels. A free body diagram shows the 4 main forces acting on a plane. You can see the engineers had to minimize the force of mg downwards while maximizing the forces of lift. The total weight of the plane was about 2,300 kilograms, or roughly the weight of a car, and the wingspan was 72 meters, or roughly the same wingspan as that of a jumbo jet. The surface area of the wings helped maximize lift, which allows the plane to coast or climb with maximum efficiency. In addition, the lightweight design minimizes the force of mass times gravity downwards. Another challenge in the design of Solar Impulse was finding a way for the plane to fly at night when it could not collect solar energy from the sun. In addition to using batteries, Solar Impulse used gravitational potential energy to help the plane coast at night. The plane would climb to a height of 9,000 meters during the day, and over the course of the night, the plane would gradually drop to a minimum height of 3,000 meters. A simple calculation shows the gravitational potential energy formula using the values of the plane. By dropping by 6,000 meters, the plane gains 1.35 times 10 to the 8 joules of energy. Another challenge was designing the plane which was lightweight, yet stable enough to withstand wind and weather conditions. The lighter the plane, the more effective it was by changes in weather and wind. Engineers had to strike a balance between stability and efficiency.
From a materials standpoint, the best way is to look at the different engineering challenges that they had to overcome to make this a reality. These being energy issues, wind, water, mold, temperature, and wing curvature. In order to compensate for the very small power input, the plane needs to be extremely light, yet resilient. The body of the plane is made from both carbon fiber and alveolate foam, having a combined density of 25 grams per meter squared. The two materials are molded together in such a fashion that gives the fuselage and the wings of the plane the rigidity as well as the flexibility required for the conditions that it encounters as the flight proceeds, and for its massive wingspan. To compensate for the wings, on the other hand, there are 140 carbon fiber ribs that line the inside of the wings, giving them their rigidity. An ultra-thin layer of polymer resin was designed to protect the top of its wings from both water and mold that would otherwise reduce the energy efficiency for its multi-day trips. The resin also protected the photovoltaic cells, which are prone to breaking, allowing the curvature in the wings and thus increasing the overall aerodynamics of the plane. The temperature problem was not entirely solved by the plane itself, as the cockpit was unpressurized and unheated. However, the insulation used was also derived from alveolate foam, reducing the temperature swings inside the cockpit from -40 to +40 down to -20 to +35, the foam again being extraordinarily light. There were also some other challenges that were not entirely met. Despite its rigidity, the plane was extremely susceptible to turbulence. This was because of its light weight and massive wingspan. Therefore, the pilot needed to have tremendous focus and vigilance. Often, on short flights, the pilot didn't sleep at all, and for longer ones, was restricted sleeping only 20-minute intervals.
In the domain of electrical engineering, the Solar Impulse project showed a revolutionary use of electric energy. Solar Impulse has 17,248 silicon cells, which produce 66 kilowatts of power. Throughout the entire duration of the flight, the cells produced 11,000 kilowatt hours of energy, which is enough to power the average American household for a year. They are mounted all along the wings, the fuselage, and the horizontal stabilizer, which totals 270 meters squared of surface area. The cells are 135 microns thick, which is the same thickness as that of a human hair. Additionally, the systems on the airplane for collecting and storing energy have been designed to minimize energy loss. The solar cells, batteries, and motors have a record-beating energy efficiency of 23% for the solar cells and 97% for the motors, which only translates into a 3% loss of energy compared to a 70% loss of energy for standard thermal motors. The energy acquired from the solar cells are stored in 4 70-liter lithium polymer batteries, which altogether weigh 633 kilograms. The batteries operate at a high voltage of 300 volts and alone make up a fourth of the weight of the entire plane. These batteries distribute electricity to 4 electric motors, which output 17.4 horsepower each. Each of the motors power a rotor, which enable the plane to fly at a ground speed of between 50 and 100 kilometers per hour. Even though the batteries have the same energy density as the batteries of a Tesla Model S, that is to say, 260 watt-hours per kilogram, the plane still flew slower at night in order to conserve energy. Also, since batteries are generally more sensitive than combustion engines, there had to be a system controlling the conditions which could affect their proper use. The efficiency and durability of batteries can be lowered if the charge they hold goes below 20%. Also, batteries are sensitive to fluctuations in temperature and should never drop below -20 degrees Celsius. An onboard system monitored the charge and temperature of the batteries in order to maintain their optimal use.
While solar technology is not ready for use on commercial jets, Solar Impulse marks the start of a clean revolution in air travel. In addition to reducing carbon emissions and reducing dependency on fossil fuel, solar energy has the potential to create long-term efficiency through saving on jet fuel. For example, a Boeing 747 jet can cost up to $140,000 to fill with fuel. With enough revision, I believe that we will find ways to use Solar Impulse's advances to create clean, cost-effective options for air travel.
Every hour, the world consumes, on average, 1 million tons of petrol. Clean technologies, such as the ones developed and tested for Solar Impulse, could cut down the energy we consume on a daily basis by 50%. More than 10 of them have already been patented and used, such as home insulation, electrical motors, batteries, solar elevators, and LED lighting.
In conclusion, we can see that the success of this project was in large part thanks to the cooperation between disciplines within the engineering profession. This is seen through the many world records that were broken over the course of the flight. Pushing the boundaries of technology is incredibly important to society in order for us to sustain ourselves and the environment. Solar power is an increasingly interesting technology which, in the near future, will enable us to reduce our fossil fuel dependency.